The Oasis Project aims to solve planetary resource scarcity by generating sustainable energy and environmental remediation through magnetic and gravitational, or MAGRAV, fields. The engine driving these fields is a state of matter called GANS, shorthand for gas in a nano of solid state. Producing field-generating GANS requires rigorous adherence to a specific nano-coating and condensation protocol. The tolerance for error is extremely thin. Even a minor deviation, introducing a trace material or slightly misaligning the electrical current, alters the physical state and the resulting energy signature. Synthesizing stable CO2 GANS requires a precise chronological sequence of chemical, electrical, and extraction steps. The successful generation of MAGRAV fields depends entirely on the precision of the nanomaterial synthesis. Preparation begins by establishing an isolated chemical environment, requiring a heavy-duty, tightly sealable plastic container. This diagram shows the base. We place sodium hydroxide across the bottom. Next, a zinc-coated wire mesh is laid over it, followed by a fine plastic separation mesh. Finally, bare copper plates rest on top, and boiling water submerges all the layers. The container is then tightly sealed. The reaction requires a minimum of 2 to 3 days, though optimal saturation can take up to 3 weeks. This specific layering sequence initiates the chemical stripping of the copper, establishing the baseline nano-coating needed to move into the electrical phase. Upon removal from the caustic bath, the copper plates will be heavily blackened. This identifies them as ready for magnetic orientation. To orient the material, we use a standard voltmeter, which must be set to its lowest possible voltage setting. This schematic details the exact polarity alignment required. The negative terminal is wired to the zinc mesh, while the positive terminal is wired directly to the blackened copper plate. The electrical contact is brief. Current must flow for exactly 5 seconds per individual piece. This 5-second pulse alignment is repeated every 6 hours for a total of 3 macrocycles. Between these electrical alignments, the material is resubmerged in the caustic bath 3 separate times to finalize the dark brown nano-coating. If the copper shows greenish or bluish tints during these initial cycles, it is simply an indicator of a normal dual oxidation process. This repetitive electrical alignment ensures the nanomaterial particles have a unified magnetic orientation, allowing them to direct electron flow during the condensation phase. With the copper nano-coated and magnetically aligned, we assemble the final CO2 condensation kit. This diagram illustrates the bimetallic pairing. A nano-coated copper plate is placed parallel to a bare zinc plate, connected at the top by copper wire. Both plates are submerged into a specific electrolytic environment, a brine solution. The salinity must fall between a 10 and 20% concentration, adjusted based on the strength of your untreated sea salt. Before reaching the plates, the brine must undergo a purity step. Passing the salt solution through a paper coffee filter strips out any foreign particulates. In a properly assembled kit, pure white CO2 GANS will condense out of the fluid and slowly settle at the tank's bottom. Achieving that white powder indicates the filtration and bimetallic pairing successfully prevented interference from foreign minerals or contaminants. The extreme environmental sensitivity of this process is best illustrated by examining a failed GANS synthesis. The error was seemingly minor. Standard steel and chrome clips were used to hold the plates. This chart shows how the chemistry was disrupted. The trace chromium from the metal clips overrode the intended CO2 condensation pathway entirely. This side-by-side comparison shows the physical result of that contamination. Instead of the white CO2 GANS, the system produced a dark red variant. This outcome reveals a core rule. Introducing different trace elements, such as aluminum, methane, or gold, will yield uniquely colored GANS with different energetic signatures. Every physical material introduced to the environment helps restructure the final state of the synthesized matter. The successfully formed Nano Solid gas is highly dense. Gravity pulls it down to settle at the kit's bottom. To prevent buildup and keep the production at maximum efficiency, this sediment is extracted every 24 hours. The extraction uses a standard syringe to pull directly from the sediment layer, removing the GANS without agitating the surrounding fluid. Immediately after extraction, the raw material is moved into a secondary isolated plastic container. The harvested GANS is then washed repeatedly with distilled water. This removes residual caustic elements carried over from condensation. Finally, the washed GANS is left to fully dry into a solid powder. This 24-hour harvesting and washing protocol ensures a continuous supply of safe GANS, ready for integration. Once dried, the CO2 GANS becomes the foundational energy source for the next stage of the technology, dynamic rotary plasma generators. By placing the GANS inside a rotating sphere, we can use a Gauss meter to track the formation of plasmatic fields, providing a physical, measurable energy output that requires no internal combustion. However, this protocol involves a critical safety warning regarding the biological byproducts of the synthesis. During production, an active protein layer spontaneously forms on the upper surface of the GANS bath. This layer is a dense chain of amino acids, the basic building blocks of life. Because it is formed in an open electrolytic environment, it remains magnetically reactive, absorbing and replicating the protein structure of any biological organism that makes physical contact with it. For engineers, the operational mandate is absolute. Do not ingest, drink, or physically touch the raw GANS or its upper protein layer. All newly synthesized materials must undergo Raman spectroscopy or equivalent laboratory testing by qualified scientific personnel before use. This protocol provides a reliable blueprint for generating plasmatic fields. Harnessing it requires respect for both chemical precision and strict biological safety.